Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fifth lecture in the lecture series on chapter number 10. This lecture will cover section 10.5 and 10.6 of the textbook. So the interface is numerical data interface. They have many different types like switches, monitors, LED displays, LCD displays, and many other interfaces can be there. So in section 10.5 is devoted to the numerical data input output interfaces. So input interfaces can be switches and some contacts and relays, and the output interfaces can be displays and devices. So here is a thumb wheel switch TWS. So it has 4 digits which can be changed from here. So maybe the first one is at the 0 place, 10th place, 100th place, and the 1000th place. Here originally mistakenly the number 1 is missing, so it is fundamentally 1000. So if we so the multiple interface allow a group of bits to the input or the output. So here this is the thumb wheel is the input and it has 4 bytes. This means it is complete one register, and if this input data we can use move instruction to display it to the output devices. So here we say that each one of the switches provided 4 binary digits, like this one from 0 to 9. This one is also 0 to 9, this is also 0 to 9, and this is also 0 to 9. So this means this is binary coded number. The BCD input allows the processor to accept 4 bit digits. Clear? So here it will maximum reach up to 10. Maximum it will reach to 9. So here the number will be from 0 to 9. This means that one BCD can represent only 10 integers, and those integers start from 0 to 9. So 0 to 9, 0 to 9, 0 to 9, 0 to 9. So this whole number can be 9999. This means 9999. So this place maximum can be 9000. This is 900. This maximum can be 90, and this is the maximum 9. Similarly, for the output display like this, so we have 1 place, 10th place, 100th place, and 1000 place, and these are connected to the LED display board. And of course here again the maximum number can be 9 and the minimum can be 0. So the total, the largest number can be 9999, and the smallest number will be 0, 0, 0, and 0. So this is the sample PLC program. The input device are the thumb wheel, and here we have these 16 bits. Each one is 1 byte. So this is maybe the 0 place, 10 place, 100 place, and 1000 place. So when we give it as a output, so again 0 place, 10 place, 100 place, and 1000 place. So to this LED, if we want to display it, we can display it over here. So move instruction can work. So suppose the destination register is LED and we can put it over here. Here we have written LED, but it can be an address in the PLC, which can the integer address. Similarly, this can be an address. So here we are writing TWS, where the thumb wheel switch is attached, and LED, the output pins where the LED has been connected. The second thing, like whenever the data in source A is equal to some data in source B, so the pilot light will become on whenever the switch S1 is closed. This means we need this should be true and this should be true. So closing S1, S1 will become true. This means it will be closed, and this means it will be true. Similarly, whenever these data TWS and source B data are equal, so this black will become true. So this operation and this operation in AND, so whenever both of them are true, so the palette light will become on. So in this case, if TWS data is 1208 and switch S1 is closed, the palette light will be on, otherwise it will be off. So on this slide, I explain the simulation of the thumb wheel by using a program of, of the thumb wheel in the RS Logix 500. So the example is the same as I explained in the previous slide. So the move instruction moves the source data to the display data, which is the destination. Whenever here we will enter 1208 and it will be equal to the source B, and this is equal instruction, so the pilot light will become on. Whenever we change it again to other number, the pilot light will become off. So as many time we change it to 1208, the pilot light will be on. So on this slide, we will explain the input module. So in the input module, we can attach an analog device, and the analog device data can be changed from analog to the digital. So analog to the digital converter over here is 16-bit. So whatever the data is there on the analog device, that data is converted to the 16-bit, and if we want to display these 16-bit, it is possible to convert them to the BCD display. But before converting to the BCD display directly, in between we need some data manipulation inside the PLC, and after that with move instruction we can display the data at the LEDs or some LCD display or some other monitors. Here you should note one thing, that whatever the input device data is there, when we bring it inside the PLC by move instruction, fundamentally we are converting the voltage to the digits. So the standard is most often from 0 to 5 volts, and in some cases it is 0 to 10 volts, and 0 to 12 volt data acquisition systems also exist. From any digital machine, whenever we calculate or synthesize a control signal, then this control signal we send it as an output signal to control some device, like over here the speed of the motor if you want to control. So what will happen, the data from the PLC we send to the from digital to the analog converter. This digital to analog converter can shift the data to analog. This analog signal can be a continuous voltage signal or a current signal, or it can be a PWM signal. In some cases it is also possible to first changing the signal from the digits to the voltage and then to the optical signal. Then we put over there isolation, and this isolation means that whatever the analog signal we have over here, we change it to the optical signal, and then once again we convert it to the electrical signal. So there is a electrical isolation between the input between the PLC or any microcomputer and the device itself. Then we have most often an amplifier which amplifies the signal which is coming from the computer, and then that signal is converted to the power signal, and that power signal can run a device like a servo motor, a heater, or any other device. So section 10.6 discusses the closed loop control. In the closed loop control system, um, the data is measured by a measurement device, and the signal from the output of the system is brought to the computing system. So over here there is a flow meter, so flow rate can be measured by the flow meter, and this signal we bring as a feedback to the PLC, and then using some controller, maybe proportional, integral and derivative controller, or only proportional or integral controller, or some other type lead lag controller, or any other controller we can implement inside the PLC. Some of the PLCs have modules for the PID controllers, adapter controller loops, lead lag controllers. Those modules are available and you can use directly. The PLC what we are using here in the classroom for the lab, it is Micrologix 1400. It has built-in PID controller. Of course, you can write your own PID controller instruction in the software using the arithmetic instructions, but doing that is slow process. So we need a little bit higher processing uh, ability of the processor to implement the PID controller computations. Then, as I explained on the previous sheet, we convert the digital signal to the analog, and then it is fed to the some type of the control element or the actuators which controls the flow. Like over here, the water flow we have to control. So if the control valve is opening over here more, the flow of the water will be higher, and whenever it is closed, the flow of the water will stop, and in between, like suppose if it is 50% open, so the flow rate will be 50%. uh, One more thing you should keep in your mind, like to this one we say the set point value. PV is the process value, like the output value, and here is the wall, like suppose it is 45% open. Here if we are seeing, this is the proportional controller value, this is the uh, integral time Ti, and this is the derivative time Td. This is the standard feedback control system loop system. This is the process. The output of this, we want to follow some desired output. If it is trajectory, we say that it should follow the desired output. If it is a fixed point, then we say the output should follow the set point. Like suppose if you want to bring the temperature of the room 25 degrees centigrade, and the AC system of the room is uh, giving the actuating the cooling effect in the room, then the output over here should be 25 degrees centigrade if the set point is 25 degrees centigrade. So whenever the set point is a fixed point, then we say it is set point, but here if the input is a trajectory, we say this is the desired trajectory. So the output of the system should follow the desired trajectory or the set point. We measure the output of the system by using some measurement system, which is sensor and the signal conditioning circuitry. The controller normally design the synthesize the control input to the system. So whenever we have PLC, so the controller synthesis process or the computation is implemented inside the PLC. So this part is inside the PLC, this is outside the PLC, and the set point is also as the output input field signal. The sensor signal is also is the input field signal. But if you want to display the output, then we can send this to the output LCD or LED display or some other monitor. So in this example, the thermocouple is used to measure the temperature of a process, and then this measurement we give as a feedback to the PLC controller. Then the PLC controller use the set point input, which can be entered using a potentiometer or some other input device. It is not necessary that it should be analog device. You can write over here some digital input keypad, and with the keypad also you can enter the set point. So internally the PID controller or any other controller algorithm is implemented, and that controller assures that the difference between the set point and the output, which is the output of the thermocouple, are as close as possible. And then it synthesizes a control signal, and that control signal is the output of the PLC, but is a input to the element, and to this signal we say the control variable. So this control variable is an input to the actuator, and the output is the process output, and most often we want to control the process output, and this process output we measure with the help of a sensor like this. So this complete is a closed loop. So the input signal is here and the output signal is here. This is why we say it is a closed loop system. This program is a closed loop on-off controller written in ladder diagram on the PLC. This heater is the output actuator, and of course with the actuator there is a drive system, and output of the heater will go to the drive system, which can be a relay or can be a switch because it is on and off controller. So here if we see, first let me explain the circuit how it is working. This is B3 colon 02. Whenever the temperature is more than this number 603, this 603 is a number which can be associated a particular voltage, and it depend upon process to process, and engineers know that what is the meaning of this 603 over here. So it is an equivalent number and representing a temperature. Suppose 603 is representing 20 degrees centigrade, or it is possible it can be 200 degrees centigrade. It depends upon the equivalency, how the system conversion has been performed. So this internal relay is normally open. So whenever this is open, so here we are using the normally close contact of the high temperature from here. So this means that whenever this relay is off, this is normally closed, and if S1 is closed, this means the heater will be on. So the heater relay is connected over here, that once it become on, then it remain on. As soon as the temperature become higher than this temperature, internal relay B3 colon 0 oblique 2 will become on. Whenever this become on, this contact will become off and the rung will be false, so the heater will become off. Here we are showing the temperature of the system. Whenever the temperature is less than the thermocouple temperature, we are sending this temperature to the source B, and again we are sending this to the source B. So the thermocouple data we always display on the LED over here. For the low temperature, whenever this temperature is lower than or equal to 597, this will be closed because this is in the excited state. So whenever this will be uh, greater than the temperature, this one this one will become automatically closed, and whenever this is closed, this means the heater is on. So we need that this should be on, and this should be on whenever the temperature become higher than 603, and this one we want to be on whenever the temperature is less than or equal to 597. This is example of the um, analog controller. So with this block diagram, it is shown that we want to control the level of the liquid inside the tank. This ultrasonic sensor measure the level of the liquid inside the tank, then it convert it to the 4 to 20 milliampere current, which is a standard for the transmission of the electrical signal. When we come very close to the PLC, we convert this signal to the voltage. Nowadays, people are sending this signal using the optical signals with optical fiber, and also with the network connected system. These signals are sent as the digital signals, and different protocols are available to convert the level to those signal. Like it can be a digital signal, it can be a analog signal in the form of current, or it can be an optical signal, or one can send it by Wi-Fi or XB signal. So we can send it in different ways to the PLC. Then inside the PLC there will be a controller. That controller can be of many different type. Those controller can synthesize a control signal, and that control signal we can resend to the control of the actuator. So again we can convert over here the signal to 4 to 20 milliampere current or some optical signal, and then when we come close to the device itself, over there it is again converted to the voltage signal to move the motors inside the actuator. So this signal over here depends upon the actuator, that which type of signal is required to actuate the actuator. Here is a brief description of the PID controller. So PID controller has three parts: proportional, integral, and the derivative. So what you do, here is the error signal. So the proportional signal originally multiply the error signal by a constant, and the integral signal take the integral of the error signal, and the derivative signal take the derivative of the error signal, and then it is multiplied by a constant, what we say kd, derivative constant. Then we multiply this one by an integral constant, what we say ki, and we multiply here the signal by a constant which is kp, proportional constant, integral constant, and the derivative constant. Whatever the outputs are there, we add them together, and then after doing some processing, we give it as an input to the process, and in response the process generate an output, and that output normally follow the set point. And the main objective over here is to bring the absolute value of this error in the vicinity of the 0. So the set point is the point where we want the output of the process should reach. So the output of the process, we say the process variable. So over here this is the level in the tank, and the PID controller is over here. The error signal is the difference between the set point value and the process variable value. The PID controller normally we implement inside the PLC, and then this generate a signal which controls the actuator. To that signal we say control variable. So these are the terminologies used inside the industry. Set point is the point at which we want the output of the system should be, and the process variable is the actual output. So in this case over here it is the level. If I want to control the flow rate, then this process variable will be flow rate. If I want to control the temperature, then the process variable will be temperature. And most often the control variable signal is a voltage signal which is given to the actuator for the actuation. The PID controller modules normally available in this shape in the market from different companies like Allen Bradley, Siemens, Omron, many other companies are there, and they manufacture the uh, PID controller modules. In the market, adaptive controllers and other controllers are also available. In the PID controller, normally inside the block, these are the things you say: the control, the process variable, the control variable, and the block length. So control means the type of the control you can select in this block, like maybe it is only proportional or proportional integral or proportional derivative or complete proportional integral and derivative controller. So this completes the lecture series on chapter 10. So we have 5 lectures on the chapter 10. Thank you very much.